Okay, Katniss Everdeen, part 3, which is asking for her, hold on, let me pull this question back up again. It says calculate the average normal force acting on Katniss as the second arrow is accelerated by the bowstring. Assume a draw length of 0.800 meters. All right, so we would just normally think, okay, so this is, we just need to get a normal force on Katniss. So we have force of gravity and we have force normal. And then we can just kind of balance them out, knowing that F net is going to be equal to the opposite of the force of gravity. So her mass at this point is 59.94. Acceleration due to gravity is negative 9.8. So if we want to put that in the calculator, 59.94 times 9.8 is going to, really? Why is this doing this? 59.94 times 9.8 is going to give us 587. So that's negative 587.412, whatever, we'll call it negative 587 newtons. So it should be a positive 587 newtons. But we have this little issue here because there is an arrow that's accelerating. So because there's an arrow that's accelerating, that's going to provide some additional forces in the equation that we have to calculate. So basically, if we look at that arrow being fired, that arrow is getting fired in with a velocity of 50 meters per second at an angle of 30 degrees. And so we have to look at this because this is generating, if they said that this is an acceleration or that we want to know as the second arrow is accelerated, we know there's an acceleration. So therefore, we've got some sort of F net acting at this angle of 30 degrees as well. So if that's the case, we're going to have to add in this little y component here from the arrow into this space here. So a problem that looked really easy just got a little bit more tricky. So if we look at this and we want to break this apart, we're trying to calculate that average normal force. So we say F is equal to M times A. And we say, all right, average force, that's what we're looking for. And then we go, oh crap, we don't have an acceleration. So we look and say, okay, well, can we calculate, how do we calculate another way? Well, we've got the impulse equation that we can use. We have F delta T equals M delta V. And we look at that and we say, okay, yes, we do have a mass. We do have a final velocity, an initial velocity. All is good. We're trying to calculate the force and bam, we run into another brick wall because we don't have time. So it looks as though we are running out of options. And in fact, we aren't. There's two ways that we can load this dishwasher. I'm going to show you the Suvat way. And then once I show you the Suvat way, I'm going to show you another way that you can do it as well. So taking a look at this given information that we have a draw length of 0.8 meters, that gives us a delta S. So a delta S of 0.8 meters, and we're looking for our time so that we can eventually, and once we get a value for time, we've got this, we can take care of this, we can take care of this. We're looking for this. So we got to get to this time, right? So we have this delta S value. We're looking for time. We don't know what our acceleration is. And we don't know, we have an initial velocity, we have a final, and we have a final velocity. So our initial velocity is 0, our final velocity is 50. So when we look at this, the equation that's going to work best for us is going to be v squared equals u squared plus 2a delta s. So we have 50 squared is plugged into 0 squared plus 2 times a times 0.8 meters. So that gives us 2,500 is equal to 1.6a. Divide both sides by 1.6. And we get our acceleration to be a big number, which makes sense because we're shooting an arrow at a very high rate of speed. So we have an acceleration of 1562.5 meters per second squared. Bam. Okay, so now that we have that, we can use this and plug that in to figure out what our time is using the, can you guys see if I do that? No, I'm going to move this up here. So we have an acceleration of 1562.5 meters per second squared. And we can take that and we can do v equals u plus at. So 50 is equal to u plus 1562.5 times t. Divide both sides by 1562.5. This, of course, goes to 0. So if we take 50 and divide it by our answer, that gives us a really short period of time, which makes total sense. So now we have a time, 0.032 seconds, and we can get this into the impulse equation. So we'll say F times 0.032 is equal to the mass of the arrow, because that's what's adding that force. Remember, we already accounted for Katniss. So we've got 0.03 times our velocity final, which is not going to be just in the we're looking at the velocity in the y direction now. So that's going to be our 50 sine of 30 minus 0. Divide both sides by 0.032. 0.032. So we go 50 sine of 30, and we multiply that by 0.03, and then divide that by 0.032, and we get a value of 23.4 newtons. So that's 23.4 newtons, and we can add that up to, put this in here, 23.4 newtons. So we're going to add 587 plus 23.4, and we get 610 newtons-ish or so. If we go back and recalculate that initial value down here, this would be at 0.4 as well. So then we would probably want to round that up to 611, but it's not that big of a deal. So now I'm sure you probably said, well, why did we stop? Or couldn't we figure this out? What force was generated by this once we got this original acceleration? And it turns out that we can. So if we look at this in terms of, so this is kind of the second way to load the dishwasher. If we look at forces, because we're looking for that average force, that's going to be equal to 0.03 times that acceleration in that y direction, right? So we can take, back up real quick. We're going to take the total acceleration here. So we're going to go 0.03 times 1562.5, and we'll get a value of 46.875. So that becomes our F net, or our force on this triangle. So we now can take that and we can work the reverse of it that way if we want to. So our force over here is 46.87 newtons, and we're trying to find the force in the y direction if this is 30. So if we go 46.87 times the sine of 30, that will give us just this piece of the y, and wouldn't you know it, times the sine of 30, ba-ba-da-da, you get the same answer. So that force of that y in the y direction is 23.43. So 2 ways to do this. The first way that I did it was I calculated the acceleration, put that net acceleration into put that net acceleration into another Suvat equation to get the time, and then plugged that into the impulse equation. And then I got the value of the force and plugged it in up here. So that's one way to do it. Or if you're more kind of inclined to look at it in terms of forces, you can take your net force and use your net acceleration, which is that big 1,562, multiply it by your mass, get an F net, but understand that that F net is going off at an angle, and we're just trying to find this y component. And once we do that, we multiply that by the sine of 30, and you guys see that we get the exact same number. So I think it's kind of cool to look at this in 2 different ways. That's why I put this up separately, because it's a little bit of a longer conversation, but it's definitely one worth having, especially because at the outset it looks like an easy problem, because you say, oh, well, we can just take the opposite of the force of gravity and count that as Katniss's normal force. But when you put that arrow in, it actually does make a difference of a good like 23, almost 24 newtons. So something to think about. If you guys have any questions, just feel free to email me over the next day or so. Hopefully this has helped you guys work these problems out. Remember, 2 of these problems are going to show up pretty much exactly as you saw them. And 2 of the other problems are going to show up in a similar format, maybe not quite asking you to do as much, but just the similar concepts are there. So if you can do this kind of stuff, then the test question should be a little bit easier. Thanks so much. Bye, team.